In this next section, I'm going to present an example calculation for a made-up exposure scenario. In this scenario, a spray adhesive is being filled into aerosol cans on an automatic fill machine line in a chemical manufacturing facility. And this task occurs about once a week, and it involves cleaning the filling equipment surfaces to remove this adhesive, essentially clean the equipment. And the workers use a rag dipped in solvent containing xylene, and the occupational exposure limit, OEL, for xylene is 100 parts per million. And the workers then wipe the adhesive using this solvent. They also use a scraper tool along with the rag and the solvent. And this cleaning task occurs once a week for about 4 hours, and roughly zero point 0.1 to 0.5 gallons of solvent are used, and the solvent has about 25% xylene. And you notice that there is some uncertainty in the amount of solvent being used, and also some uncertainty about how much xylene is there in the solvent. The room dimensions are known. They are 20 feet by 40 feet by 12 feet. But the general ventilation rate, again, is about 6 air changes per hour, but we're not that precise about that. And there's no other local exhaust ventilation in this room. So we can go ahead and use the well-mixed room model. So we know the volume of the room. So that turns out to be, after unit conversions, 272 cubic meters. The ventilation rate, if we go with 6 air changes per hour times 272 cubic meters, the volume of the room, divided by 60 minutes, is 27.2 cubic meters a minute. And the mass rate of xylene, so let's assume that we are using half a gallon of solvent, so we convert the gallons into liters, so multiply by 3.78. You convert the liters into cubic centimeters, and then you multiply by the density, which is 0.88 grams of solvent per cc of solvent. And then you convert the grams into milligrams, and then 25% of that is xylene, so that you multiply by 0.25. And you divide by 4 hours, so that's 240 minutes. So the mass emission rate of xylene is 1,732 milligrams per minute. And we can plug it into our IH mod spreadsheet, and we would get this time profile of xylene concentration in the room as a function of time. So in this graph, we see that the xylene concentration increases till about around 50 minutes or so, and then it reaches a steady state value of 61 milligrams per cubic meter. And the TLV for xylene in milligrams per cubic meter is 435, so that corresponds to 100 parts per million. And so we are well below that exposure limit if we use the well-mixed room model. We can now also use the near-field, far-field model. So again, the volume of the room and the air changes through the room and the mass rate, they all remain the same as before. But now we calculate the volume of the near field as 2/3 times pi r cubed. And the r, if you remember, is taken as roughly an arm length, or about 0.8 meters. So the volume of the near field is about 1.1 cubic meters. And the air flow rate between the near field and the far field can be calculated as shown here as 6 cubic meters per minute. And we can plug these into the near field, far field model, and we get, for the far field, the same steady state concentration, 61 milligrams per cubic meter, that the well-mixed room model predicted. But in the near field, we get a much higher concentration of 348 milligrams per cubic meter. So now this near field concentration, it's getting up there. It's getting close to the threshold limit value, or TLV, for xylene of 435. But we might be a little unsure about what is the effect of various model parameter uncertainties on the near field concentration. Could it go up beyond 348? So we do some uncertainty analysis. One simple way to do it without using Monte Carlo simulations is to say, okay, we know that, for example, the solvent use is somewhere between 0.1 and 0.5 gallons per hour. And so how does the near field concentration change if the solvent use was 0.1 gallons per hour? So we see that actually the concentration goes down as you would expect. So if you're using less solvent, the airborne concentration you would expect to be much less. And so it does reduce by almost fivefold. But now let's do a more thorough uncertainty analysis for the near field. And at this point, I'm going to just, to keep things interesting, change my units. So rather than do it in units of gallons, I'm going to use the amount of xylene used in units of milliliters. And so let's assume that the xylene used can be described by a log normal distribution with a geometric mean of 200 milliliters and a geometric standard deviation of 3. And the percent xylene in the solvent can be described by a uniform distribution with a minimum of 10% and a maximum of 50%. Previously, if you remember, we had used 25% as the sort of chosen value. The ventilation rate we'll assume is described by a triangular distribution with a minimum of 5, a maximum of 7, and a mode of 6 air changes per hour. These are graphs that show visually what we are assuming. So this is the log normal distribution describing the amount of xylene used. This is the uniform distribution showing the percent xylene in the solvent. And this graph shows the triangular distribution showing the ventilation rate. If we now run through a Monte Carlo simulation with 1,000 trials, what I'm showing here is the output of the Monte Carlo simulation. So on the x-axis, we have the actual airborne concentration. On the y-axis, we have the probability density function. And the histogram are the realizations of the Monte Carlo simulation. So what we are saying is that the geometric mean for this is 38 and a geometric standard deviation is 3.5. So this is well within the threshold limit value for xylene of 435 milligrams per cubic meter. So if we use reasonable uncertainty parameters, we realize that actually this is not a worrisome exposure scenario at all. And so that's what uncertainty analysis can help us do. It can provide us more realistic estimates of the exposure distribution and also more realistic assessment of what the risks are in a given exposure scenario. And with that, this lecture comes to an end. What I would like everybody to do is also look at the Camtasia unit that describes how to use the Monte Carlo spreadsheet and software using the simulation software in Excel.